Good afternoon by Louis-Pierre Arguin from Montreal and New York on maxima of log-correlated Gaussian fields and the Riemann Zeta function on the line.
Thank you very much. Thank you to the organizer for this very nice conference. So what I want to talk about today is joint work with David Bellis, who's at NYU, and Adam Harper, who's here, and they're both in the audience. And Adam is the number theorist on the project. So the subject is the maxima of log-correlated Gaussian fields and the relations to the Riemann Zeta function on the critical line. Okay. So the purpose of this talk is twofold. First is to advertise a really nice conjecture by physicists, three physicists, Fyodorov, Hyry, and Keating, okay, that relate the maxima of the Riemann Zeta function on the critical line to the maximum of log-correlated Gaussian field. And the second purpose is to advertise a model that we're going to work with, a model for the Riemann Zeta function, and was introduced by Adam not so long ago, and where you can actually predict, I mean, it's a model that is more tractable maybe than the random matrix models. Okay, so those are the two purposes. So this is going to be a talk about maximum, so I just want to talk about extreme value theory. So just to set all the notations and the purpose. So I'm going to have often random variables xi's, okay? So you have n random variable xi, some probability space, and we're interested on some functional of this stochastic process. So for us it's going to be the maximum, not the sum, just the maximum. And the standard problem in extreme value theory is to understand the distribution of the maximum. So you would like to find a recentering term an and maybe a normalization term bn so that you have convergence in law for this maximum. Okay? So heuristically you can write the maximum as some an, the recentering term, which will be deterministic in our case, and the fluctuations are at the scale, so the bn controls the size of the fluctuations, and m is just the law of the fluctuations. Okay, so this talk is going to be about the deterministic order an of the maxima. Okay, a bit like in the was mentioned in Nicholas' talk. So that's the setup, and here's the outline. So we're just going to study first the case of ID random variable to warm up. Okay, just to as a benchmark. I'm going to mention branching random walk. They have been mentioned quite a bit today, and log-correlated Gaussian fields. Okay, so that won't be too new for you. And then I will talk about number theory, and I will mention the conjecture of Fyodorov, Hyry, Keating. So we have a random model for zeta that we'll talk about that was introduced by Adam, and where we can actually prove a big part of that conjecture. And another question, I'll finish with that, a conclusion. So there was a nice talk yesterday by Boris Korysenko on characteristic polynomials of random matrices. So there's a very strong link with my talk with the conclusions, where you look at the maxima of a characteristic polynomial of random unitary matrices. Okay, so that's the program. So let's start with a maximum of ID random variables. So that's very simple. So here's just a simple picture that's white noise essentially. So I just put on the interval 0, 1, 2 to the 10 Gaussian random variable. I have some variance which looks a bit weird first, but that's going to be the choice of the variance that will be relevant for the Riemann Zeta function. So 1/2 of the log of the number of random variables I have. Okay, so I just put 2 to the 10 random variable on 0, 1, and that's one realization. And what we're interested in, I'm not sure if everybody can see that, is the highest peak, which is essentially around here. Okay, so this is an example of a stochastic process. I mean, we have a random landscape or a random energy landscape, and you want to understand that in general. This is the case of independent, and then you can look at cases of where the variables are correlated as some other types of energy landscape, and that's going to be the case for zeta and for the random matrix problem. Okay, so let's just start very simply with the case of ID random variable, which sometimes is called the RAM model, random energy model introduced by Derrida in statistical physics. So here's a simple proposition that is an exercise. So if I have, now I'm going to pick a certain normalization which is convenient, so I'm going to take 2 to the n random variable, okay? And I'm going to take a variance for this ID Gaussians. I'm going to take a variance which is linear in n with some parameter sigma square. Okay? So this is a convenient parameterization because the recentering term then is the first order of the maximum is a constant time n. So the maximum is the first order is linear in n. Okay, linear in the variance. And then you pick up the subleading correction that Nicola mentioned in several problems, okay, which is logarithm of n, and there's a constant in front which depends on the sigma square, this parameterization. C is this explicit first order, didn't mention the explicit velocity of my linear term, square root of 2 log 2 sigma for my parameterization, and I get the 1/2, okay, for ID random variable. And so, and with that normalization, the fluctuations are of order 1, so that's why it's convenient. And then what you can show is that the maximum, when you recenter by this deterministic order, it actually converges to a double exponential distribution, or Gumbel. Okay? So that's very simple. So I can write the max as deterministic order and some fluctuations. Okay? So how do you prove this? And this is not hard to prove because the probability that the maximum is smaller than the levels, the probability that every one of them actually are smaller, so you have nice factorization. And in the end, if you write the proof, it boils down to the convergence of this object, which is the expected number of points, okay, that are high, so that reach the level an plus some fluctuations. Okay, so that's what is called number of exceedances in the first book on statistics of extremes, written by Gumbel in 1958, and I think it's still the best book on statistics of extreme. It's a really nice book, really nicely written. Okay, so you want to show convergence of the expectation of number of exceedances. Okay, so that's how you prove the case of random ID random variables. Okay, so again, you can check. I mean, that was a picture I had before. I'm sure not a lot of people can see, but the highest peak was a bit above 6. Okay, and if you look at the deterministic order for the, I had 2 to the 10 random variable with a certain variance. If you plug that in, you get 6.35. So that's always nice to see that everything is working. So the idea now is that, okay, that's easy, but you would like to have such a method, or such a method, such techniques for correlated fields. And now we have nice heuristics, a nice approach that was developed by a lot of people for log-correlated Gaussian fields. Okay, so that was the case for ID random variables. So let's go to a case that is slightly more complicated, but now we know more and more. Is the case of branching random walk. Okay, so we saw this tree several times today and during the week. So here's my notation for the branching random walk. So I'm going to take a very simple branching random walk, okay, on a binary tree with Gaussian increments. So my notation here is x and v. Okay, so my field, my random variables are indexed by vn, and vn are the leaves of the binary tree. Okay, so I have 2 to the n random variables, and you do the natural thing, which is to associate to every edge ID normal random variable with mean 0 and variance sigma squared. That's my parameter that I will adjust later. Okay, so the field associated to that leaf is simply the sum, obviously, of all the random variables on the path from v to the root. Okay, so that's a simple Gaussian field indexed by the leaves of that binary tree. Okay, so YL will always denote increments in my random walks in this talk. Now the variance is easily calculated because it's a binary tree of height of length n, so I will have sigma square n for the variance. For the covariance, that's getting a bit more interesting. For the covariance, if I have leaves v and v prime, okay, so that means the path at some point branched out, so they branched out at some level, okay, and the covariance is simply the variance of the common part of the path. Okay, so because the blue part after they branch out, obviously they're independent. Okay, so that's simple enough. So this field is log correlated because one way to see it is if I fix V and I look at the neighborhood, okay, so if I fix V and I look at the number of points V prime that are correlated, say, they have some covariance which is bigger than sigma squared k, so they branched at level k. This thing, it's easy to see, okay, so those, in the end, I'm looking at the size of a certain ball, so it's all the points that have the same ancestor at level k, and it's just 2 to the n minus k, I'm sorry, okay, and I actually can send this 2 to the n on the other side, okay, and just looking at the proportion of points in that neighborhood, and this proportion of points is 2 to the minus k, okay? So if you think of those neighborhoods, if I embed my tree on 0, 1, if I embed this tree on 0, 1, and I think in terms of intervals, in terms of the size of the balls, how these neighborhoods behave in the size of the ball, they have to, okay, decay logarithmically with the inverse of the distance, okay? So that's why this branching random walk is a log-correlated model in the end, okay? So this is the case of the branching random walk, the definition of the model. And now here's a theorem that a lot of names are associated to this theorem. I will mention them later. So if I look at the maximum now of this Gaussian process, so the maximum of x and v's over all my leaves, then again it goes linearly at first order, goes linearly in n, like linearly, yes, in n. And I have the constant c, which is exactly the same constant as for independent random variables. So you don't see the correlations, okay, at the first order of the maximum. Okay, same velocity. And you have to go in the order log n to actually see the difference with independent random variable. And the difference is that 3 that you pick up, okay? And so that 3 is related to a nice mechanism that I will mention again, but Nicola mentioned it with a barrier of a random walk. And that goes back to Bramson, was the first read to solve such a question. And you have, and after that, you actually pick up the fluctuations which are of order 1 again, okay? So 2 important remarks. The first order is the same as ID, as I said. Second order differs, okay? And also the fluctuations will differ, okay? So we know now in a couple of models that the fluctuations should be like mixture of Gumbel, okay? So here's some names. So there's a lot of even recent results on this exact law of the fluctuations. So for branching Brownian motions, I mentioned there's the seminal work of Bramson, then Lally and Selke, Bachman, and Dario and Reed, Ely recently, and recent paper by Branson, Ding, Zaituni. And then you also have results on the joint law of the extrema, so the extremal process. And there's work by myself, Bouvier and Kissler, and Aidecon, Berestecki, Brunet, and Shi. And Madol did it, so we did it for branching Brownian motions. Madol does it for branching random walk. And this is a question about 0 temperature. I'm looking at the maximum, but as we saw in Olivier's talk and also in Thomas' talk, you can look at the Gibbs measure, so it's a positive temperature problem. But usually the level of the difficulty is similar. Okay, so there's work by Derrida and Spon, Bouvier, Korkova, and Barral-Rod-Vargas for the Gibbs measure, okay, of the energy landscape that you get for this log-correlated Gaussian field, okay, for the branching random walk. So that was for branching random walk. So now what's a log-correlated field? So it goes back to my little remark I had on the board here, that actually the definition we have is that it's a definition which is approximate, doesn't have to be exactly log-correlated, but the covariance should actually decay like the logarithm of the inverse of the distance, here normalized by the number of points. Okay, so it doesn't have to be exact. Gaussian free field is actually not exact because you have boundary effects in particular and finite size effect, but it's approximately logarithmically correlated. Okay, so there's a lot. There's a 2-dimensional Gaussian free field, Gaussian multiplicative chaos. There's also conformal loop ensembles in that universality class. And what this talk is about is the Riemann Zeta on the critical line and the characteristic polynomial of unitary matrices. So that's what we expect. Actually, what we expect is that if I look at the maximum of these processes, okay, it should actually behave, if you choose your parameter right, the sigma square, you should see the same constant in front, the same 3 here, the 3 is universal, and even the fluctuation should be a mixture of Gumbel, okay? So that's like the ideal case. So this is proved in a couple of cases. Maybe the model where there's more progress is a 2-dimensional Gaussian free field. So going back to Bolthausen, Dershel, Jacobin, that calculated the constant, showed the same as ID, the first order, and then nice work by Branson, Diggs, Zaitouni, who showed the convergence of the maximum, and Biscup, Lido look at the joint statistics of extrema, okay? And there's a nice work by Elie Heidekon on the extremal process on conformal loop ensembles, and also a lot of work on Gaussian multiplicative chaos, looking at the Gibbs measure, okay, of these objects, okay, as again seen as an energy landscape, okay. So that's, okay, in a nutshell, what the universality class of log-correlated field is when you have some correlation, some covariance that essentially decay logarithmically with the distance, behave logarithmically, and the universality class should have the same constant here, the 3, and the fluctuations of order 1 mixture of Gumbel, okay? So now let's go to the Riemann Zeta function, okay? And let's look at it as a log-correlated process, okay? And I mentioned the conjecture of Fyodorov-Hayek-Keating. So that's a picture of the Riemann Zeta function, the modulus, okay, on the critical line. And you see that it oscillates quite a bit, which is a good thing if you're a probabilist, okay? But there's also a growth, which is kind of almost deterministic, some envelope, okay? So what can we say about this object? So first, what's the Riemann Zeta function? So the Riemann Zeta function defined for when the real part of S is bigger than 1 to ensure convergence. It's just the sum over the integers 1 over ns, okay? And you can write this as an Euler product, so a product over prime of 1 minus p to the minus s to the minus 1, and the relation between the two is just the decomposition into primes of every natural number. So this object makes sense if the real part of S is bigger than 1, and Riemann showed that it can be analytically continued to the whole complex plane via this functional equation which relates the real part of S bigger than 1 with the real part of S smaller than 0, okay? So you know everything about this function in this part of the complex plane, everything here, and we don't know much about the critical strip, and that's what you want to understand, okay? So there's some coefficient here. When this coefficient is 0, which is negative integers, odd integers, then you get trivial zeros, and the questions about the zeros, the big questions that I won't answer today, is about the zeros in the critical strip. I answered that question right away. Okay, so the prime number theorem can be shown if you show that the zeros are strictly inside the critical strip. Okay, so you rule out 0 and 1. So if you show that closer and closer to the symmetric axis of the critical strip, which is real part is equal to 1/2, then you get better and better information on the distribution of the primes. So the prime number theorem, and we'll need that input in our model, is the following. So if I write pi x as the number of primes smaller or equal to x, so it's like the CDF of the prime if you want. This is the logarithmic integral of, so the integral of 2 to the x, 1 over log x, and there's an explicit error term, okay, that goes back to Adama de la Vallée-Poussin, okay, so x to e minus c squared of log x, okay? So the good way to think about it is 1 over log x is the density of the prime, okay, so we'll need that. And the Riemann hypothesis that says that 0 is exactly on the critical axis, the critical line, real part is equal to 1/2. What happens is you get a better control on the error term, okay? Goes from x to the e minus c square root of log x to square root of x, essentially log x, okay? So this is a two slices in the Riemann Zeta function, so we're interested in that object. And what will be important is this density of the prime, and also that we have an explicit error term, okay? And we actually need that in the computation. So what kind of questions do we want to answer? Okay, so obviously not all of them, but so what we're interested in is how large is zeta on the critical line. So that itself is a really hard question, okay? So the Lindelof hypothesis tells you that if I look at the global maxima, okay, so at this envelope here, then it grows slower than any power of t as you move t on the line, okay? And the Riemann hypothesis improves that a bit. So it's not so clear actually what's the order of the maximum, okay? These hypotheses just tells you that it's, at most a power of, it's smaller than any power of t, but it's not clear what's the correct order. Okay, so obviously this is a kind of a deterministic question, if you wish. It's kind of deterministic envelope. If you're a probabilist, you see they oscillate quite a bit, so there's some noise there. And if you see some noise, you expect some limit theorems, okay? And what we're interested in is actually how large is zeta in a bounded interval, okay? So this picture obviously is not super useful except for the fact that you realize that it's quite of a noisy function, okay? So this is at the level 10 to the 7 on the line, okay, for some bounded interval, okay? So it's almost like white noise. And what we're interested in are the maxima on this bounded interval. The zeros are the one when you have singularities, but we're away from the zeros because we want the maximum, okay? So that's what we're interested in, but we want some randomness, right? So what you're going to do is you're going to pick your interval, your bounded interval, uniformly on the critical line, okay? So one way to do that is to pick a point uniformly on the critical line, say between t and 2t, okay, big T. I'll take the interval 0, 1 plus, okay, this tau, which is picked uniformly on that critical line. Okay, so that gives me a probability measure, so you can look at the process, which is, instead of the modulus, we're looking at the log of the modulus of zeta, okay? For that tau, for that random interval, okay, 0, 1, where you pick the location. So you have to introduce some randomness. And here's the conjecture, okay, of maybe that's the most important slide. This is the conjecture of Fyodorov-Hyary-Keating. So the answer of Fyodorov-Hyary-Keating is the following. So if I pick tau again uniformly on this line, and I look at the maximum on some bounded interval, say 0, 1, then the log of the modulus of zeta should go like log t minus 3/4 log t, and fluctuations of order 1, okay? So there's a lot of logs, but, okay, first time you see that, what is striking here is extremely precise, okay? They actually guess the explicit constant, and they even say that the order 1 should be like log-correlated, so mixture of Gumbel essentially with a right tail, which is x e to the minus x, okay? So they're very, very precise in their conjecture. Now, this is just numerology at this point. What's the comparison with branching random walk? So it turns out that you have an exact match for the constant, okay, if you choose your parameter correctly, okay? So for the first order, I had square root of 2 log 2 sigma. Here I have log t. I have minus 3/2 sigma squared over c log n. Here I have this guy, minus 3/4 log t, okay? Now, if I want to have a match, one way to do that is the following. So if I say that log t is like 2 to the n, which is my number of points in branching random walk, and I have picked my variance sigma square n, if I pick it to be 1/2 log t, okay, then you realize that you actually have a perfect match. You can make the calculations. So actually sigma square should be log 2 over 2, okay, to have an exact match. So at this point, this is just like playing a game, but I can justify these choices, and that's what I want to convince you, okay? So the point is, again, that you have an exact match between branching random walk and the maximum of the modulus of zeta if you pick your parameter correctly, okay? So their conjecture, they made the conjecture using the random matrix model, okay, where you can do more calculations than with zeta, okay? And they have also the conjecture on the random matrix model. I will mention that at the end. Okay, but their conjecture is based on that. They have some numerics. Okay, so you might laugh that the numerics to pick up log t. Okay, they have to be very, very good. Okay, but they have actually really convincing numerics for at least the first order. And also the numerics go to 10 to the 35 on the line, which is much better than 10 to the 20 that was a threshold for some time. So Hierarchy, so we were speaking to Keating, and Hierarchy has method to actually go up to 10 to the 35. And by the way, the error term doesn't change sign, okay, and the distribution of the prime up to that level. So that's kind of amazing. So that's how they justify the conjecture. Now let's look at more elementary connections, okay, that can actually at least motivate this conjecture and show that actually it's a reasonable one. So first of all, it's not a Gaussian process. The process on 0, 1 is clearly not Gaussian. Okay, so why do you see log-correlated Gaussian field appearing? It's not so clear. Okay, and why did I pick this a parameter which is exactly sigma square log 2 over 2? Not so clear either. Okay, why is it log correlated? It's not clear either. And here I have a maximum over a continuous process, whereas for branching random walk I had a discrete process. Okay, so there's some things to justify to make the bridge between the two problems. So I'll spend just 3 slides explaining those bridges, okay, and then I'll talk about the random model. So first of all, this is not a Gaussian process, but there's a central limit theorem. So instead of looking at large deviation, large values, you can look at the typical value at one point. And that was done by a really nice result by Selberg CLT. So if I just pick a point randomly on the line uniformly, and I look at log of the modulus, and you normalize properly, and the good normalization is square root of 1/2 log t, then you converge to a Gaussian variable, a standard Gaussian. Okay? It's an amazing theorem. Okay, and then you see already that the fluctuations of that, of that landscape, the marginals are Gaussian. Okay. So for T large, this is essentially Gaussian, and also it tells you that every point has a variance 1/2 log t. Okay, which is exactly the variance you need to make that match. Okay, so that's a good thing. So that explains, at least motivates a bit the choice of the variance. Okay, so if I have log t is equal to the n, the match of the number of points, then the variance, okay, I should pick sigma squared to be log 2 over 2. Okay, so that's the first bridge between the two. Now you could ask, this is the CLT for one variable. What if I look at multivariate CLT, and that was done by Paul Bourgade. So Paul showed that if I, again, look at this process, so that's process that interests me in a compact interval, in a bounded interval, and I normalize by a square root of 1/2 log t, so it's really the multi-dimensional equivalent of Selberg, then he shows that this converges, but in finite dimensional, in the sense of finite dimensional distributions, to Gaussian fields on 0, 1 with log correlations. Okay, so what that means, if I pick 2 points on 0, 1, okay, and they are, let's say, at the level log t, the distance between them is log t to the minus alpha, okay, so it's kind of like a logarithmic distance. If I take the log, so in the end, in the limit, these fields have covariance alpha, okay. So this is a multi-dimensional, multivariate central limit theorem, but this is not strong. This is a very weak convergence, not strong enough, okay, to use this to say something about maximum or large deviations. Okay. So that's the result of Paul. Okay, so that takes care of 2 bridges. Now, this is a continuous process. So if you want to make the link with branching random walk, you will have to show that you can discretize and essentially discretize your interval to partition your intervals and show you don't lose much. Okay, if you look at the maximum in each interval. Okay, so you have to prove some sort of maximal inequality. But so what happens is, okay, so what happens is this function oscillates quite a bit, but obviously this is still a continuous function with singularities at the zeros. But if you focus, okay, deep enough, if you zoom in, you're going to start seeing some irregularities, okay? So the question is, you have to zoom in to what scale to actually see the irregularities, okay? So it turns out that, and we can prove that for the random model I will introduce in the next slide. But if you want to prove the conjecture for zeta itself, you will have to prove some maximal inequality, okay, in some definite interval, and should be interval of length 1 over log t, okay? So 1 over log t in my correspondence is 2 to the minus n, okay? So it's exactly if I take 2 to the n points, okay, on the interval 0, 1. So, and then you would like to show that, okay, so on this interval, okay, you have some continuity, so essentially you're locally constant, okay? Okay, but this maximal inequality can only be true close to the maximum, right? Because you have singularities, so you have to prove this close to the high points. Okay, so those are the three motivations for the conjecture. And here's maybe the strongest one, which is we can prove it for a slightly different version than zeta, okay? So here's our random model for zeta, which is different than the random matrix model. Okay, so let me explain it. So the connection is quite simple. It's simpler, I would say, than random matrix theory, where the connection is a bit more mysterious. So remember that I could write zeta as an Euler product. Okay, so if everything converges, okay, so I'm for a large real part, so the log of zeta I can write as the sum over primes, the log of 1 over 1 minus p to the minus s. Okay? So what you can do is say, well, for p large, this guy is small, let me just expand. And so if you expand the log, what you're going to get as a dominant term is p to the minus s, okay, plus something of order 1, okay, for s. Obviously, this holds, okay, rigorously only if the modulus of s is large, or the real part of s is large. Okay, so the connection, so what you would like, so it's not clear that this connection is true for all s, okay, but what you can do rigorously is a result by Sundararajan, and it was adapted by Harper in his first paper, is that if you assume the Riemann hypothesis, okay, and that holds for h and tau on the critical line of large probability, okay, there's some technical assumptions here, but this essentially says that this is actually correct up to order 1. So the log of the modulus of zeta, okay, on the critical line at the point tau plus h is the sum over primes, but I have a cutoff, okay? I have a cutoff at big T, okay? So I sum the primes up to big T, and I have a real part of p to the minus I tau, p to the minus IH, okay, divided by p to the 1/2, okay? So if I take the modulus of this, I get the real part of that. So this is the rigorous statement, okay, of this short calculation, formal calculation, okay? So that's the connections, our rigorous connection, if you want, to the Riemann Zeta function, okay? So that's actually a nice observation by Adam, okay? So now, where's our model? So you have these p to the minus I tau, okay? So p to the minus I tau, this is just a phase, okay? This is a random phase, and tau can be quite large, okay? And it's an easy calculation. You can do it by yourself, that if I look at this process, which is p to the minus I tau for all p primes, this converges in finite dimensional distribution sense, again, to uniform ID random variable on the unit circle. So, okay, so this p to the minus I tau, okay, for tau large, tau is random, this is where the randomness comes from. It's a phase, the random phase, and converges in some weak sense to uniform random variable to the unit circle, and they're independent for different primes, okay? So that's the rigorous connection to the zeta, and here's the modeling part. We'll replace those p to the minus I tau by these UPs, okay? So that's our model for the Riemann Zeta function, okay? So it's the sum over primes. It's a cutoff up to t, okay, big T. The real part of now, these UPs were the p to the minus I tau, p to the minus h divided p to the 1/2, okay? So that's our model. Any questions on this model, okay? So the calculation to keep in mind is this one. If you just replace this, the same thing, and we replace the p to the minus I tau by uniform, okay? And now we have a stochastic process, okay, on 0, 1 that you can fully analyze, okay? So our main result is the proof of the conjecture for that stochastic process. So if I look at the maximum of the stochastic process, okay, this, the sum, the real part of UP is p to the minus IH, okay, h is on 0, 1 divided by p to the 1/2. Then first order goes like log t, like for branching random walk, minus 3/4 log t, okay? And we are not able to get fluctuations of order 1, okay? So it's with lower order terms in log t, okay? So that's the main result, and I must mention that the first order was actually proved by Adam in his first paper, okay? But to actually get the second order, that's what I will explain, you actually have to introduce branching random walk techniques, okay? You have no choice. And one interesting part of the paper is actually this approximate branching random walk that we see in this model should also be there for the Riemann Zeta function, okay? So that also outlines at least an approach or a program to actually prove the conjecture for the Riemann Zeta function itself. Okay, so how do you prove the second order in general for branching random walk or for an approximate branching random walk? So Nicola mentioned that this morning. So what you want to do first is to actually find the scales. Okay, so for branching random walk, I could write every random variable in my field as a sum of increments YL. Okay, and we think of L as the scale going 1 to n. So the scales are actually the levels in the tree. Okay. And there is a nice, what I call dichotomy of correlations, okay, for the increments, and that's clear for branching random walk. The only thing that means is like we have a branching point in branching random walk, and for these 2 points, the increments are fully correlated before the branching point, and they decouple after the branching point, right? So the correlations are, so before the branching point, they're actually fully correlated, and after that, they're independent. So you want to see such a picture in your stochastic process, in particular in this random model of the zeta function. So, so here's how you do it for that model. So finding the scales is usually not so easy, okay? And once you have the scales, you can apply the program of branching random walk, and now, I mean, it has been done for quite a lot of models, so you can just use the machinery. So in our case, so now let me just write 2 to the n, make the correspondence log t is equal to 2 to the n. Okay, so I'm going to work as if I had 2 to the n points, like a branching random walk. Okay, so I have the sum over all the primes whose log is smaller than 2 to the n. It's like p smaller or equal to t of these random variables. So one mistake would be to think that each of those random variables, since they are independent, the UPs are independent, they must be the increment, okay? They are not the increment, okay? Because here the increments were IID, right? They had variance, okay, of the same order, variance sigma square, okay? So you want to have increments that actually are the same at every scale. So the right choice in this problem, and that should be also the right choice for the Riemann Zeta function, is actually to bunch up the increments together. So we take the increments which are, so for the increment at scale L, we sum over the p's whose log is between 2 to the L minus 1 and 2 to the L. Okay, so the point is that you have to bunch up several increments together to actually have variance of essentially order 1. And that's a short calculation. You know all the laws of the UPs explicitly. So if you do the calculation, you're going to pick up 1/2 sum over the primes in that interval, 1 over p. And since you know the density of the prime, you can actually know with that error given by the prime number theorem, what is this sum of 1 over p. Okay, so the density is like 1 over log p. So in the end, when you do that integral, that calculation, you get that every increments have a variance of log 2 over 2, okay, plus something of little o of 1, okay? So bunching up all the primes together, you get actually a variance which is essentially constant along the scales, and that's important to apply the analogy with branching random walk. So that's the first ingredient, and the second ingredient is you want this phenomenon where the correlations, you have the branching points, and before the branching point you have the same increment, and after you decouple. So again, it's not a hard calculation, okay, because you know explicitly the law of the UPs, okay? So the branching point that you define is defined in terms of dyadic distance, okay, because you're log correlated, so that's the right thing to do. So you define the branching point between h and h prime to be 2 to the minus branching point is equal to the h minus h prime. Okay, so my notation h wedge prime is for the branching point, I should say. And if you define it this way, you realize that the increment for the branching point, okay, for the scales which are before the branching point, they essentially like the variance plus an error term, but the error term actually decays exponentially with the scales, and that's important, okay? And after the branching point, you're not perfectly independent, but it's an error term that decays again exponentially with the scales, okay? So the picture that you have is not exactly like a branching you have in branching and random walk, but you have some gray zone, okay, before, after, and after the branching point, where these error terms have, you know, they have a substantial contribution, but the contribution decays exponentially, okay? So that's important because you can control the error, okay? So that's the approximate branching random walk, and you know explicitly the error in that case, okay? So now how do you do, it's the same recipe, so I won't enter too much into details because Nicola mentioned it quite a bit this morning, but what you want to do is not look exactly, so let's pick 2 to the n points on the interval. So I want to look to the n points on the interval. What I want to look at is the number of points among these 2 to the n that reaches a high value, so the high points, and I want to count those number of points, so it's the number of exceedances. But that's not the right thing to do because of this 3/2 that you have. You realize because of correlation, if I look at the expectation of the number of exceedances, it's going to diverge as opposed to IID. So what you want to do is look at a modified number of exceedances. And the input, as Nicola mentioned this morning, the input comes from the insight you have on the correlation structure, okay? So for branching random walk, you know that at every level of the tree, you have a branching random walk. So its maximum at every level cannot go beyond L times some velocity. And you have the same thing here. So what you do is you modify the number of exceedances by the event. Okay, you add the event that the sum of all the increments for every scale has to be smaller than L, the number of increments times log 2. Okay, so at every scale L. Okay, so that's the idea. So that's the number, modified number of exceedances. Okay, so you count the number of points that are high, but at the same time avoid this barrier, which is the line C times L. Okay, so at every scale. So again, this comes from the insights you have from the correlation structure of the maxima. This is what you do for log correlated. If you have more complicated models like the Sherrington-Kirkpatrick model, for example, then you will have to have a deeper insight of what's going on for the correlation structure of high points. But something like that should also be true. Okay, so and how you prove it then, it's just upper bound and lower bound on these number of exceedances you have modified with the barrier event, okay? So then it's just classical standard probability. For the upper bound, it's just Markov inequality, and for the lower bound, you use Palais-Zygmunt inequality, okay? So let me just say two more words on the proof, because, I mean, there's some technicalities that arise from the fact that you don't have a clean decoupling, okay, like in branching random walk. So there's maybe a couple of ways to get around that. The way we use is, so that's one problem. And also one other problem is this random walk we have, the sum of the increments, they're not exactly IID, okay? Because you have an error of little o of 1 for the variance, okay? So it's not a perfectly a random walk with really IID increments. They're not identically distributed, but they're close to IID, okay? So the way to compare between this approximate case and the clean case of branching random walk is to use just a Berriesian approximation, okay? And since we only need 1 point and 2 point because we use first moment and second moment method, that's not to, that we can actually apply this Berriesian approximation only on 2 points, and it's quite a good approximation. And so once you, so we have those random walk, we go to the Gaussian world, okay, so they have now Gaussian increments, and in the Gaussian world, you can compare explicitly processes just by looking at the covariance matrices. So it's an explicit comparison result, if you want, okay? So there might be other ways around this, that's the way we do it, okay? So just going to the Gaussian world. So those are two technicalities in the proof I wanted to mention because that might arise in other problems, okay? So I will skip the proof with the barrier because it has been explained quite a bit by Nicola how you get this 3/2. Because I want to have some time to talk about the random matrix model. So it's another time model for the Riemann Zeta function, and it's related to the talk yesterday by Boris. So. And it's also an open problem, so it's kind of nice. So here's another energy landscape, another stochastic process. So what this is, it's actually on 0, 2 pi, not 0, 1, but that doesn't matter. So what this is the log of the modulus of the characteristic polynomial of a random unitary matrix. The size is 2 to the 10, like I had at the beginning with, I had 2 to the 10 IID random variables. And this random unitary matrix is sampled uniformly with the Haar measure, okay, on the unitary group. And if you see, okay, just the punch line, I guess, I take the size of the matrix is like the number of ID variables I had at the beginning. I guess you cannot see here, but I'm interested in the maximum. It's a bit above 6, okay? The punch line is actually that the first order, again, should be like ID random variables, okay? So this is a nice random landscape. You also have singularities here, which will be at the eigenvalues. Okay, so that's essentially the explanation. So just the definition, characteristic polynomials, just the determinant of 1 minus e to the minus I theta times mn. So theta is now my parameter. My interval is 0, 2 pi instead of 0, 1, okay? So if you actually plot, so this is I don't know what the size of this matrix is, but it must be less because it's more regular, okay? And the process you're interested in, again, is the log of the modulus of this object, and theta runs on the circle on 0, 2 pi, okay? And that's the conjecture of Fyodorov-Hayek-Keating for this problem, and that's actually the way to actually motivate the conjecture for the Riemann Zeta function, because it's believed that it's a good model. So the characteristic polynomial of a random unitary matrix is a good model for the zeros, okay, for the zeta function actually on an interval, okay? So they have, so there's some numerics on that. So obviously the numerics for this conjecture is much better than for the zeta function. So the conjecture is as follows. The maximum of the log of the modulus of the characteristic polynomial goes like log n is the size of the matrix, minus 3/4, which is the same constant as we had for the Riemann Zeta function and for our random model of zeta. Log n, something something of order 1. So it's exactly the same thing as for branching random walk again, and Riemann Zeta function, and the connection between the two now is that you have to pick n to be log t, okay? So n is 2 to the n with the connection branching random walk. Again, you have exact match, okay? Everything is open essentially for this problem. The first order is open. There's, so this log n, there's the first, there's the equivalent of Selberg's central limit theorem, nice result by Keating and Snaith. And you have the equivalent of the result. So Bourgade showed that this process, properly normalized on 0 to pi, converges to a log-correlated process in terms of finite-dimensional distribution, so the multi-dimensional equivalent of Keating and Snaith. And there's a really nice result by Webb, okay, for the Gibbs measure. So again, I can see this as an energy landscape, rugged energy landscape. So I can look at its Gibbs measure. It's a positive temperature result as opposed to a 0 temperature result at small beta. So it's actually at high temperature. And he shows a connection to Gaussian multiplicative chaos and related to the talk of Thomas Madon. Okay, so that there's some results in that direction. Okay, but essentially everything is open. So how would you approach this problem for the random matrix? So the first thing you would like to do is to find the scales again. Okay, so the scales now are suggested. Again, you can, like here, expand the log, okay? And if you expand the log, what you are going to end up with is the sum over all the j's between 1 to infinity, the real part of the trace of mn power j e to the minus I theta j divided by j. It's a bit like the Fourier series of this log characteristic polynomial. And you see that what replaced by UP's or my p's to the minus I tau is the trace of the power of the matrix, okay? So those are the random variables here. And so it's very tempting, if you want to study the problem, to actually define the increment a bit the same way we did for the Riemann Zeta function. So instead of looking at each term of this sum as the scales, you actually consider several j's together, so you bunch them up, okay? So and how you can calculate the variance, you can use results of Diaconis Shashahani, very nice classical result now, that, and they tell you actually that if I take trace of power k times trace power j, okay, complex conjugate, the expectation of that is delta kj, so they're orthogonal for different powers, and you have some norms, the minimum between k and n, okay? So if you use this nice result, actually you realize that the variance, if you bunch up again, the variance is essentially constant plus some error term. Okay, so it seems to be the right thing to do. But one problem is that the increments, the YLs, and the trace of the powers, they're orthogonal because of this result, but they're not independent. Okay. So you have orthogonality of increments, but not independence. These things are not Gaussian, so that's a different problem. Okay, so it's not so clear what you can do here. I want to mention a nice paper by Hughes, Keating, and O'Connell, where they actually studied the large deviation of the log of the characteristic polynomial, and they get 1 point large deviation in the right regime, but they don't get 2 point. Okay. And since the method is based on a second moment, you essentially need 2 point large deviation for the lower bound, and this you don't have, okay? So that's missing, okay? So my last slide, just to going back to the conjecture about zeta itself. So I think for probability, by the way, sorry. So for probability, this is a nice conjecture, okay? This is well-posed random matrix theory, no number theory here. So this should be doable, but that might be quite hard. And to go back to the conjecture of we started with Fyodorov, Hyry, Keating. Okay, so this is for the log of zeta. The first order obviously is open, otherwise I would do my talk on the first order. And but there is results. Okay, so it seems hopeless because there's zeta in the name, but it's not hopeless. There are large deviation results available. Okay, and there's a nice paper by Radziwill on large deviation. It doesn't really So it depends. You kind of get large deviation in the right regime for the truncated sum, but not for zeta itself. Okay, so thank you very much.
Everybody's stunned.
So what is the best that's known in zeta? Anything?
For the maximum?
Yeah.
So let's see. For the bounded interval, you can get an upper bound. So for the first order, there's an argument where you can get the upper bound and the lower bound.
But that doesn't give you Lindelof's hypothesis because it's
No.
because of
That's
tau.
weaker. Yeah.
Because of tau, right?
Yes, I mean, it's also because I look at the bounded interval, right? So Lindelof is about the global maximum, the whole thing.
Can you calculate some of these sums using some results in probability theory? Once you know, once you define this sum with the random walk, this sort of sum over the primes, can you, if you work out the limiting behavior of this random variable, can you use it to calculate the sum that you want, taking the variance or something, or?
Yeah, that's essentially what we do.
And you manage to calculate some of the sums?
Yeah.
This is the first time that I've seen other models for the zeta function than the random matrix one. Is there a whole zoo, or is this just
I guess the number theory, and Adam might be able more than me to answer that question. I like this model because it's simple and
So in your approximate model, you replace things by the ID variables on the circle. So actually, how far is this p to the negative I tau from IID? Is there any knowledge on?
so that's a good question. Okay, so it's not hard to show that it converges in finite dimensional distribution. That's to calculate the moments. Okay, so they're actually really close in the right sense, right? But what you're asking is that you have to control the whole sum at the same time. Okay, so I don't know how strong you can lift that convergence. Not so clear to me actually. But in the right sense of convergence, they're exactly the same in the limit.
Well, then let's thank all the speakers of today again.